The most interesting star, I think, the star that could be shocking in our sky is this one, Betelgeuse or Betelgeuse. It's a red giant star.
The geomagnetic storm of the decade, as you might have noticed from a few weeks back, sometime around May 10th, marked one of the greatest series of geomagnetic storms Earth has experienced in the past 2 decades. These storms, visualized by the Space Weather Prediction Center, brought about an extraordinary sight, the most impressive aurora borealis ever experienced in the extreme ends of both the northern and southern hemispheres. These auroras, captured as far south as Hawaii in the northern hemisphere and as far north as Queensland in the southern hemisphere, flooded social media with breathtaking images. Stick around to delve into why these auroras were so extraordinary. Normally, the appearance of auroras isn't considered strange, but when they're seen so far from their typical locations, whether in the far north or south depending on the hemisphere, it becomes a remarkable and unusual occurrence. This sets the stage for the absolute marvel of this phenomenon. Greetings, wonderful people. I'm Anton, and I'm thrilled to have you join me on this scientific journey to explore this event further. We'll uncover its significance, understand the science behind auroras, and examine a prediction made in a crucial 2019 paper. But before we dive in, let's take a closer look at an image that showcases our fortunate timing. Meet sunspot R3D 664. These events typically originate from the heart of a sunspot, and in this instance, that sunspot is known as R3D 664. It's a superactive sunspot that recently emitted another burst of energy. However, this time, the emission was directed away from Earth. Displayed here is one of the images captured by a satellite of the National Oceanic and Atmospheric Administration (NOAA). Among the Sun's many spots, R3D 664 stands out as a massive object, one of the brightest and most expansive sunspots seen in this solar cycle. Spanning almost 200,000 kilometers, it dwarfs the Earth, being 15 times wider. Its visibility, even with inexpensive eclipse glasses, makes it a focal point for educational and outreach initiatives, sparking curiosity about solar physics and space weather. Sunspot phenomena like R3D 664 offer a prime example of their significant impact on solar events. They emerge as cooler regions on the Sun's surface, shaped by intense magnetic activity that suppresses convection. This magnetic activity often results in sudden energy explosions known as solar flares, which we delve deeper into in our YouTube video about solar flares and the complexities of Solar Cycle 25. R3D 664 has showcased its remarkable output by generating multiple M-class and even X-class flares. These powerful solar eruptions emit electromagnetic radiation waves that propagate across the solar system, manifesting as sudden spikes in radiostatic or causing issues with communication and navigation systems on Earth. Moreover, various coronal mass ejections have been associated with this sunspot. These remarkable solar occurrences involve the outflow of massive gas bubbles and magnetic fields from the solar corona. The trajectory of these coronal mass ejections increases the likelihood of colliding with Earth's magnetic field, triggering geomagnetic storms that could disrupt satellite communications and power supplies. The recent activity of sunspot R3D 664 underscores how stars wield immense power, capable of profoundly impacting modern technological developments. This disruptive potential highlights the importance of closely monitoring sunspots like R3D 664 to precisely track their features. To achieve this, scientists employ a variety of instruments, including terrestrial solar telescopes and space-based observatories like NASA's Solar Dynamics Observatory. Through an analysis of this sunspot's formation, motion, and magnetic characteristics, scientists can glean valuable insights into the mechanisms driving these solar phenomena. These discoveries are crucial for safeguarding vital infrastructure, such as power networks and satellites, from the unpredictable nature of the Sun. They also enhance the precision of space weather forecasts. Observatories and scientific institutions worldwide are seizing this rare opportunity to educate the public about the dynamic nature of the Sun and its profound effects on Earth. As we approach the peak of its 11-year activity cycle, even those without access to telescopes can witness sunspot R3D 664's rotation and changes over time. Monitoring this sunspot yields invaluable insights, underscoring the significance of celestial phenomena and their profound impact on our technology-dependent society. The most recent observation by the National Oceanic and Atmospheric Administration revealed one of the most powerful solar flares witnessed in decades, all originating from this sunspot in a span of a few days. What's particularly alarming is the rare announcement by NOAA regarding the potential for a powerful geomagnetic storm, akin to the feared Carrington event, resulting from these emissions around May 10th. Comparisons to the Carrington event are drawn due to similarities in the strength, size, and characteristic release of a significant amount of components when facing Earth. This Carrington-like event, categorized as a G5 storm, occurred twice that weekend, striking Earth with a series of 5 coronal mass ejections and multiple solar flares. The Carrington event of 1859 emitted the strongest geomagnetic storm ever observed, causing sparks in failing telegraph systems across North America and Europe, with some sparks severe enough to ignite fires. The parallels between the Carrington event and R3D 664's recent activity serve as a stark reminder of the potential for solar interference to disrupt Earth's technological infrastructure. R3D 664, with its strong flares and coronal mass ejections, presents a modern-day threat comparable to, or even more severe than the Carrington event. The recent sightings of auroras as far north as Queensland, Australia, and as far south as Cuba offer a vivid depiction of the underlying geomagnetic processes. Researchers and scientists closely monitor these auroras, recognizing the potential dangers they signal. Strong movements in Earth's geomagnetic field could herald widespread electronic disruptions. As a beacon for understanding current solar activity, the cultural and scientific significance of the Carrington event persists, sparking discussions about the potential for widespread blackouts or internet outages. The intricate network of modern society, heavily reliant on magnetic stability, remains susceptible to solar storms akin to the one that occurred in 1859. Methods developed post the Carrington incident, like reinforced electrical grids and satellite shields, depict ongoing efforts to mitigate future risks. Plans for global preparedness leverage insights gathered from monitoring sunspot R3D 664. International organizations such as the United Nations Office for Outer Space Affairs and the International Space Weather Initiative spearhead efforts to forecast and mitigate space weather effects. The potential recurrence of a Carrington-type event, with modern infrastructure in place, poses a genuine threat beyond breathtaking aurora displays. Sunspot R3D 664, behaving similarly to the 1859 event, suggests that any modern-era event would be larger and more violent. With today's interconnected infrastructure, widespread blackouts, lost GPS signals, and malfunctioning satellite communication networks are conceivable outcomes, potentially causing significant economic repercussions. Despite dire predictions, technological advancements since the 1800s have bolstered our ability to address similar crises. Advanced predictive models and real-time monitoring satellites aid in the development of early warning systems. Strategies are being devised globally to manage extreme space weather events, including simulations to assess infrastructure resilience. Reflecting on R3D 664 serves as a reminder of celestial bodies' tremendous power and the importance of preparedness. Studying and observing R3D 664 reveals our vulnerability to cosmic events while offering crucial insights into solar physics. Through scientific research and vigilance, we strive to better prepare for future challenges. Join us as we explore ways to mitigate risks associated with and prepare for such extraordinary events. In 2003, we encountered a phenomenon similar to this, known as the 23 Halloween solar storms, which caused significant damage and power outages in countries like Sweden and South Africa. Although recent concerns were raised, no such damage occurred. However, during such storms, satellites may encounter major issues or even fall out of the sky due to the expansion of Earth's atmosphere, influencing their orbits dramatically. A good example of the susceptibility of satellites to solar storms is evident in SpaceX launches. Previous solar storms resulted in the loss of a few satellites, but this time, luck was on their side, with no reports of satellite damage or major disruptions to power grids. However, unusual irregularities, such as temporary disruptions to GPS systems, were reported in the United States. In 2003, as Halloween approached, a series of alarming events unfolded throughout our solar system. Unexpected sunspots appeared on the sun's surface, signaling turmoil within. Approximately 3 and 12 years had passed since the sun's last violent eruption, occurring at the peak of an 11-year cycle of solar eruptions. Despite precautions taken during earlier incidents, the scope of what was about to happen was unprecedented. The sun unleashed a series of enormous explosions known as coronal mass ejections (CMES), launching massive clouds of electrified gases into space. Solar telescope observations recorded the largest known release of solar X-rays, flares shooting thousands of miles into space. and a jet stream of charged particles traveling at staggering speeds. The Earth found itself in the crosshairs of this cosmic onslaught. The Halloween storms on Earth produced some of the most spectacular auroras ever seen, signaling dangerous electrical phenomena. These solar storms wreaked havoc on the world's power systems, causing kilovolts of electricity to surge into the atmosphere. Despite their breathtaking beauty, the storms damaged communication satellites and disrupted systems, including a GPS-based air navigation system, leading to a 30-hour outage. Beyond Earth, the impact of these solar activities reached the Mars Global Surveyor, damaging its radiation monitoring equipment, and affected the Voyager spacecraft, which was on a mission to the outer reaches of the solar system. While the extent of damage was limited this time, it raises questions about our preparedness for future events. The similarity between this event and the Carrington event, coupled with a lack of significant damage, raises intriguing questions. Was it merely luck, or were preparations made after the 2003 disruption effective? Sunspot R3D664's resemblance to the historic Carrington sunspot adds complexity to the situation. Considering its massive size, the National Oceanic and Atmospheric Administration labeled this event historic, highlighting its significance despite minimal damage. This prompts further inquiry into why no significant damage occurred, raising questions about our level of preparedness for future events. The importance of studying such events becomes evident when considering predictions made in 2019. Contrary to previous studies, which suggested a weak solar cycle, the 2019 study indicated a very strong cycle ahead. This highlights the importance of continued research and preparedness in the face of potential solar disruptions. The discrepancy in solar cycle predictions sparked fascinating discussions, explored in a video featuring a younger, less jaded Anton. According to the study, significant emissions and a potential geomagnetic storm might occur around 2024-2025. Recent observations hint at a solar cycle potentially lasting 22 years, challenging the traditional 11-year cycle. The significant solar event in 23 suggests the possibility of similar events around this time. Despite expectations of a strong cycle, the peak is projected for 2025. While the solar spot responsible for recent phenomena has moved away from Earth, reminiscent of the Carrington event, breathtaking light shows have occurred in certain regions. These displays, unseen for almost a century, underscore the potent nature of such occurrences. Before concluding, let's delve into how auroras work and why they exhibit various colors. Auroras result from interactions between Earth's magnetosphere and solar emissions. Highly charged particles interact with the magnetosphere, settling in regions around the Earth's magnetic field lines. Collisions with gases in the upper atmosphere, particularly nitrogen and oxygen, produce vibrant colors. When oxygen molecules in the upper atmosphere ionize, they emit green light predominantly. Under exceptionally powerful solar emissions, ionized oxygen can transition to a rare red aurora if undisturbed for at least a minute. Nitrogen, on the other hand, produces blue or red light, often resulting in a magenta hue. The interplay of these colors provides insight into the intensity of the solar event triggering the aurora. Red auroras, in particular, are rare and elusive, appearing only on select occasions. Understanding these phenomena enhances our comprehension of solar activity and its effects on Earth's atmosphere. Auroras, those breathtaking displays of light, begin to manifest about 120 miles or 200 kilometers above the Earth's surface. At these altitudes, oxygen atoms are prevalent, but the atmosphere is incredibly thin, making sightings of red auroras challenging, especially at high latitudes. However, under ideal conditions, high solar particle concentration and low wind speeds, spectacular displays of all red auroras can illuminate the highest parts of the sky. These mesmerizing auroras are primarily caused by collisions between electrons, activating oxygen atoms and propelling them to higher orbital levels within their atomic structure. Instead of instantly returning to their initial state after absorbing energy, oxygen atoms hold onto this energy for an extended period, possibly up to 2 minutes at elevations exceeding 400 miles above the Earth's surface or 200 miles above sea level. As this stored energy gradually releases, it appears as a vibrant red light, creating a characteristic smearing effect in the sky. Red auroras have long been of cultural and scientific significance, particularly in the Mediterranean region, due to their unique color and visibility from considerable distances. While human vision struggles to perceive these red auroras accurately, digital cameras can capture their full range of light, including their elusive red hues. Viewers are encouraged to explore dedicated videos to understand the distinctions between human perception and camera recording of auroras. On rare occasions, viewers may also witness captivating displays of blue auroras, typically occurring at the beginning or end of the auroral season. These displays, limited to transitional periods when astronomical darkness prevails, offer insight into the dynamic interaction between solar winds and Earth's atmosphere. In conclusion, while this solar event was exceptionally powerful and produced various effects in the upper atmosphere, it miraculously caused no harm. However, it underscores how much we still have to learn about the Sun and its cycles. As we approach another solar maximum, preparations for potential disruptions, such as power outages, are prudent. Improved communication from organizations like the National Oceanic and Atmospheric Administration would be beneficial in providing advance warnings of impending events. Caution and readiness are essential in light of recent severe solar activity. That concludes today's video. Until next time, ciao.